Hello learners, this class is for BSc Physics Sem 2 students. In this class we will see what is PV diagram. Okay, we'll learn what PV diagrams are and how to use them. We use them to find the change in internal energy, to find work done and to find the heat. Okay, so we'll use it. We'll see what are PV diagrams. Okay, now consider a gas which is kept in a cylinder with tightly fitted. It has a piston on it, so we can do work on the gas by pressing the piston downwards and upwards, and we can heat the gas also by placing that cylinder or the container in which the gas is there over a flame, or whatever we have to do. That means we are subjecting this gas to thermodynamic processes. We are making some thermodynamic processes to happen on the gas. So in this process what happens is pressure and volume of the gas will change. Pressure changes and volume changes. Okay, so we can show this pressure and volume changes on a diagram, okay, or on a graph. Okay, so let me draw a container in which there is gas and we have a piston over here. Okay, let this be some piston. Okay, we can move this piston up and down to compress the gas and to expand the gas. Okay, or okay, let this be some piston. Okay, to compress the gas or to expand the gas, we are using this piston. Okay, a convenient way to see the changes in the pressure and volume is by the diagram. Okay, that diagram is called as PV diagram, or it is also known as indicator diagram. Okay, indicator diagram is nothing but, in the graph we take pressure and volume. Okay, pressure on y-axis and volume on the x-axis. So okay, we'll see the different states. Pressure taken on the y-axis, volume taken on the x-axis. So we'll see, when we press the piston downwards, okay, when we press this downwards, what happens to the volume? The volume get decreased. Okay, the volume of the gas will decrease. So the state must shift to the left. Okay, and because of the smaller volumes, since the gas is being compressed, so the graph will be in this way. Okay, let this be some initial state, and after compressing let it be some final state. Okay, this is a diagram of the gas being compressed. Okay, for sure we can say the gas is doing some work, the work is being done on the gas, so work done will be positive. Okay, work done will be positive. Similarly, when the gas is expanded and when we take the graph, or when we draw the indicator diagram, we can see that gas is being expanded, and we can visualize on the graph in this way. It was on the initial position I, and after expanding it will come to the final state F. Okay, in this way. Okay, here it was like this. Understood? Okay, initial states to final states. Right? So here this is the expansion of gas happening. Expansion of gas happening. And what about the work done? Work done will be negative. Okay, understood? If we let the gas expand, we have to push the piston upwards, upward direction. The volume increases, the volume of the gas increases, so the state must shift to the right towards larger values. Okay, So for sure we can say that work is being done on the gas. So work is negative. W is equal to negative. So if we ever see a state that is shifting to the left on a PV diagram, we can say the work done is positive. And if we see on the right, then work done is positive. Sorry, negative. Right? Now how do we now we can also see a cyclic process when we, so let this be figure 1 and let this be figure 2. Let's draw the curve 1 and 2 together so that they constitute two processes that bring the gas back to its initial state, like this. Okay. This was first curve, whatever it is. Okay, but this is cyclic process, initial and final position. It is coming back to its initial position. Okay, the gas is brought to its initial state. So such a series of two or more processes like this represent a closed figure, which is called a cycle. So the area within this cycle, or the area within this closed figure, is obviously the difference between the first curve and second curve. It also represents the network done by the cycle. So here also we can write W is negative when the volume increases. For second figure, volume increases because of the expansion of the gas, no? And here volume decreases. Okay. Now can we find out the magnitude of the work done? We have seen the signs, right? W is equal to positive when the gas is compressed. W is negative when the gas is expanded. And we have seen that by visualizing the PV diagram, right? So here the total network would be positive as network is done on the system here. Okay, now let us see, can we find out the magnitude also? Now we will see, can we find out the magnitude of the work done from a PV diagram. So the work done during a thermodynamic process is, you can see here, again we'll draw the indicator diagram. Now the gas was at this stage initially, okay, and the gas was here at the final position, okay, right? VI, VF. So we can say that the a shaded rectangular region here, okay, the shaded rectangular area gives the work done. Okay, work done is equal to the area under this curve. Why? The reason why work is equal to area under this curve is because we know W is equal to force into displacement, right? Force into displacement. Let us take displacement as x. Okay, force into displacement. Now we know, or work done, let us take dW, right? So dW is equal to force exerted by the gas and distance moved. Okay, force exerted by the gas and the distance moved. So force formula, we know force formula, right? Pressure into acceleration, because as we know, P is equal to F. I'll write here. As pressure is equal to force by area, we can write force is equal to pressure into area. So I have written force is equal to pressure into area, and this x, okay, the distance moved, let us take it as dx. Here it has dw, here it has here we have tried it as dx. So dw is equal to pa into dx. Now this, I can write this expression as dw is equal to p into a dx. What is a dx? A is the area. Okay, A is the area. Area means length into breadth, length into breadth, and let this dx be some height. So length into breadth into height. This a dx becomes length into breadth into height. So how we can write it? Length into breadth into height is nothing but volume. So change in the, we can take it as change in the volume. So dw is equal to pdv, right? dw is equal to pdv. This is the formula. And if you want the net the total work done, the entire in the entire process or in the entire states, the total states, so we can write like w is equal to integration from initial state to final state pdv. Okay, initial state of volume to initial state of final state of volume, w is equal to pdv. Okay, we can either get w is equal to pdv integration and dw is equal to pdv. Either of the expressions are correct for the work done. So in this way we have also found out the work done, the magnitude of the work done using PV diagram. So how the area under this curve shows the work done, that is dw is equal to pdv. This is very important formula or expression. You have to remember this, dw is equal to pdv. So that's it about the PV diagram. We'll meet in the next class. Thank you.